Good afternoon, good evening, morning, welcome. We'll make a start. Welcome to the constellr webinar on calling our cities, the role of LST data for effective heat island management. My name is Charlie Siggs. I work for constellr and I'll be moderating this webinar today. We have a fantastic lineup of speakers who will be sharing their knowledge and expertise on the importance of satellite-derived land surface temperature data for monitoring and managing urban heat islands. A few house rules before we begin. Questions will be answered at the end of the webinar. We have a dedicated Q&A section. Please put all of your questions into the Q&A tab at the top of the webinar. And if you have any questions that are specifically for one of our speakers, please can you name who that person is? And also that this webinar will be recorded and will be made available afterwards. I'm pleased to introduce our speakers for today. We're delighted to be joined by Joachim Maes from the European Commission, also Elsie Ibrahim from constellr, and Mattia Rigiroli from Latitudo 40. An overview of our agenda for today. We will be starting off by covering how the European Commission is monitoring and learning about urban heat islands, and then moving on to how we are acquiring land surface temperature from space and how that is important for urban heat islands. And then Latitudo 40 will be covering how that data is then used in the heat island analysis at a local scale. Then moving on to the future looks like and constellr's satellite constellation, which we'll be launching later this year. And then finally moving on to the Q&A section. And up first, we have Joachim Maes, who will be presenting how the European Commission is monitoring and learning about urban heat islands. Joachim has worked as a policy analyst for the European Commission's Directorate General for Regional and Urban Policy since 2021 in the Unit for Policy Development and Economic Analysis. Before, he was a scientist at the Joint Research Centre and supported the implementation of the EU Biodiversity Strategy. He is a marine fish biologist by training. Joachim, the floor is yours. You're on mute, Joachim.
Sorry again. Thank you, Charlie. A good afternoon indeed from Brussels, where I work for the European Commission for the cohesion policy, essentially. Under that policy, we use the long-term structural investment budget of the European Union to essentially make sure that regions don't drift apart economically and socially, or that less developed and rural regions are not left behind. So we invest in these regions, but in other regions as well, to implement EU policies. As for today, so I'll brief you a bit on what is currently the EU policy on climate change adaptation. I have just also one slide on our possible intervention options to address climate change impacts through adaptation, and then I dwell a bit on our data needs to assess urban temperature, in particular extreme temperatures during summer. The EU is well known, I would say, for its policy on climate change. It is a European climate law, which sort of hard codes our commitment to become climate neutral by 2050, to reduce our greenhouse gas emissions with 55% in 2030 from 1990. And we do that through the European Green Deal, where we set sort of hard targets on energy use, energy efficiency, renewables, but also on greenhouse gas emissions. In contrast, I would say the policy on climate change adaptation is more a soft policy. There's an article in the European climate law that wants EU countries simply to adopt and implement national adaptation strategies and plans. And also there's an accompanying climate adaptation strategy, which is more about making commitments, stimulating countries to set up plans on climate adaptation. There's no hard targets, as we know, for energy and for greenhouse gases, for instance. And I think, I mean, that's partly due to the fact that whereas we can quite well capture climate impacts in numbers and data, it remains difficult to come up with a quantitative assessment on what climate change adaptation actually is and how we have to implement it. So hence we don't have real numbers or targets to do that. So hence also the importance of this seminar to ensure that we have better data. And I mentioned then also that besides climate policy, there's also research policy and a space program through Copernicus with, of course, the delivery of very relevant data to monitor the climate. What can we do? We intervene through the EU budget, which is roughly 1/3 that goes to cohesion policy, and managed by the DG where I am a staff member of. 1/3 is agricultural policy and 1/3 are all other EU priorities. In this financial framework, there is room for climate adaptation measures, essentially under agricultural policy and the Fund for Rural Development, but also substantially under cohesion policy, the European Regional Development Fund and the Cohesion Fund. Specifically for urban areas, we have an instrument called European Urban Initiative, where countries or where partners, organizations, institutions, regions can apply for funding, for instance, on urban greening and tackling urban heat islands. We offer also through our budgets specific support to regions and cities to increase their preparedness, to awareness raising on climate change adaptation, capacity building in their administrations to learn how they can set up projects to increase resilience of cities and regions to all kinds of climate change impacts, flooding, forest fires, droughts, but also extreme temperatures in cities. Specifically to give an idea on where adaptation currently stands relative to mitigation, and we spend about 90 billion structural investments for a 7-year period, which is topped up by co-financing from countries to about 115 billion euro. Most of these investments still go to mitigation actions. About 15 billion is foreseen for climate adaptation actions, and in the middle, you have nature-based solutions, which I mean can be implemented in such a way that they sequester carbon and contribute to mitigation, but nature is also important to help us adapt to climate change. Plus, we have a small crisis support instrument to help countries with post-disaster relief. For instance, this year we had the devastating climate or floods in Slovenia, forest fires in Greece on the island of Rhodos, and then we also intervene. There's an urgency for more data on urban heat island and also on mitigation, how we can deal with it. This is a paper we did with the JRC 2 years ago, where we mapped globally an indicator called SOHI, so Surface Urban Heat Island. And it is calculated as the difference between urban temperature and the temperature in rural areas. That difference is increasing almost everywhere globally. So cities are warming up much faster than the countryside. That's also the case in Europe. The only place where we see an opposite trend is in the deserts of the Middle East and Africa, where the countryside is desert and therefore also warms faster than cities. But again, a message that urban heat islands are going to be a key problem in the next decades to come, and that we will have to address this. What are our data needs? Last week, the European Environment Agency published its EU climate impact assessment, and it warns that we are insufficiently prepared against the impacts of climate change, and so too, so too the Covenant of Mayors assessed that many cities, even if they are aware about the risks of current and future extreme heats, are not taking or insufficiently taking action to address this problem. So what we need is more harmonized, consistent, and regularly updated high-resolution surface temperature data for us at EU level to analyze the extent and the trends of urban heat islands. And if we do that, we use our urban typologies to allow comparisons, more on this in the next slide, and we ensure that data integration is possible. We don't map urban heat islands just for the sake of mapping, but we want to know where are vulnerable populations at risk. So do we have data also by age or by income, or where are specific services at risks? Think about healthcare facilities or schools which might suffer from extreme temperature. Urban typologies are important to us because they allow us to compare cities, regions, or the countryside across Europe. Here there's 3 examples of these, which are also officially adopted as typologies by Eurostat. So we discriminate predominantly urban regions from predominantly rural regions. We have a typology for functional urban areas, which has a definition for what constitutes a city and its surrounding commuting zone. And then we have a degree of urbanization on the right-hand side, where we use a 1 kilometer population grid to again discriminate between cities, towns and suburbs, and rural areas. Typologies are used for indicators and allow us indeed to compare and see where problems are eminent or most important across Europe. In the context of this seminar, I just mentioned 2 important policy initiatives for urban heat islands. Hopefully next week the Council will adopt the very final vote of what is called the nature restoration law in Europe that has been heavily debated by countries and by the Parliament. But in that, there is a target on urban green space. So we want the minimum level of urban green space in cities. We want urban green space to also increase over time, especially with a view on helping cities reduce extreme temperatures. And more importantly, and a bit aligned to this new nature restoration law, there is a proposal from Eurostat, also a regulation to for a mandatory reporting by countries on the impact, the cooling impact of urban green spaces. In another paper with a illustrated on the right-hand side, we propose such a methodology which uses land surface temperature data in combination with data in cities to calculate how urban green spaces, trees, and urban forests cool down cities. And again, this is going to be a mandatory indicator for countries to report to Eurostat. Finally, a last slide here. We work, or we certainly from our department, we are we do efforts to develop on the medium term an urban climate service that would need to deliver long-term trend data on urban heat islands to monitor changes in extent and in temperature, so to allow us to understand how big is the problem and will it change. We see there also the development of tools for local and regional administrations to help these with monitoring or forecasting urban temperature so that they can either react on events or plan ahead with respect, for instance, to urban greening. And we hope on the medium or the longer term that we can host such a climate service as part of Copernicus. Thank you for your attention.
Thank you, Joachim, and for that presentation, and very interesting to learn about the data
and
requirements.
Now I hand over to, yeah.
And so, yeah, thank you, Joachim, for that really interesting presentation and for learning about the requirements of the EU policies when it comes to satellite LST data and implementing those, and what's required for the municipalities across Europe. So now that we know more about the EU policies for UHIs and their data needs, how do we acquire satellite LST data? What can it tell us about urban areas and what is currently available? To cover this topic, I'd like to introduce Elsie Ibrahim from constellr. Elsie works in the product team. She has a decade of experience in research and academia. In 2020, she moved into the private sector. Her academic journey from bachelor to doctorate was in civil and water resources engineering. She strives to make a positive impact on the world, constantly having environmental and social challenges at the heart of any mission she embarks on. Beyond her professional life, she is a mother of 2 curious kids who are re-educating her about the world. She is active in organic farming and cannot survive without sunshine or music. Elsie, please tell us more about satellite LST, how it is acquired from satellites today, and why it's important for urban heat monitoring.
Good afternoon, everybody, and thank you, Charlie, for this introduction. So I will start just by aligning really well with the previous talk, is about the need for monitoring. We saw with the previous talk that there is an urgency for urban climate understanding and for mitigation of urban heat island. And in fact, of course, as also mentioned, greening is a critical aspect of that, urban greening. And with this urgency as well, we have seen that there were really great initiatives also being tested and tried all over the world, from very high-tech approaches, for example, to shading towers of Abu Dhabi, or the shading policy that you can see in the second figure between green spaces and shading elements in Sevilla, to painting streets in white of LA, and to, for example, the green roof paths in Rotterdam. There have been a lot of interesting things done. The problem is that we really need to move from these small initiatives to make them scalable. And that's why monitoring is very important, to understand, for example, where to locate these initiatives, the site selection aspect of it. Also, as previously mentioned as well, we need to quantify the cooling impacts of any of these, be it initiatives or be it at a larger scale. Also, we need to be able to intervene in case there is a problem, a failure of any of these systems. And so this is why space data becomes part of the story. And this is why satellite data becomes an embedded element of this story for urban climate. So today we are talking about something quite specific, actually. So we're talking about land surface temperature. And we're talking about that coming from space, so acquired by thermal sensors. So in this part of the talk, I will briefly explain what it is and why it is relevant. And then after my talk, there will be Matteo who will talk about how it is being used for the urban context. So let's try to help Matteo to bring us there with this explanation. So this land surface temperature, actually, it's radiative temperature. So it's not really the temperature often we are used to. So many people try to compare it directly with the ambient air temperature from weather stations or from ground sensors that are at a certain depth. But in fact, of course, this comparison is quite crucial to get a lot of insights, but it's not really the same temperature. And the radiative temperature as well is very interesting because it also embeds in it characteristics of the material we are looking at. And that's very interesting and very important to keep in mind. So how is this data actually retrieved using satellite systems? So you have the satellite platform that's acquiring the thermal data. And then this is then downlinked through the ground segment and then sent to another segment for data processing, from which we have an LST retrieval algorithm that gives us the LST data. So this data processing, as I mentioned, since LST has information of the surface area you're looking at, so you have to include that in this LST retrieval. So you have information on the land cover, on the topography, but as well, you have information on the atmosphere at the time of acquisition of the data, because the data, the signal has to go back to the satellite, has to go to the satellite acquired by the satellite. So the state of the atmosphere interferes in that as well. Once this processing is done, then we have the LST data. And in fact, it's not only a value, it's a geospatial data. So these are what we refer to as images or maps, however you are used to working with them. But then also we have a lot of supporting data coming with them. So we have flagging of faulty pixels, for example, cloud and shadow masks, uncertainty layers, metadata that can help the user to analyze the data easily. So these are all part of what we refer to as this LST retrieval. So LST being used for the urban environments has already had a great heritage. So you already saw a lot of examples from the previous talk using that. And the reason is that LST provides really a unique insight in the composition of urban areas, which is a very complex blend of vegetation, water, bare soil, and impervious surfaces. So this blend needs to be identified in a good way with the different types of urban areas. LST is really one of the key elements there. And many applications of LST have allowed us to find risky areas with urban heat, but also shady spots for refuge. Also, it has allowed us to compare different cities and the impact of urban planning. Also, within a city, we have been able to compare different neighborhoods and in the context of this thermal inequity due to different economic constraints for different neighborhoods. You have more risk for this heat. So all of this has been done with LST and often has been done with public missions. And here I would like to show the public missions, how they are placed within this current sphere. And at the same time, I will show also where constellr's future mission is located within that sphere. Before we go through that, I really would like to just mention that there is always a trade-off between the different characteristics of these satellite missions. And depending on the main objectives of the mission, the optimal selection of different characteristics is chosen. So when we talk about spatial resolution, temporal or the revisit time, and when we talk about also the coverage, they are all intertwined within a selection of trade-offs. So when we look, for example, at the top left at MODIS and Sentinel-3, we can see that they have a relatively lower resolution than the rest, reaching 1 kilometer, but they have a high frequency, a high temporal resolution. So reaching a day or sub-day revisits for MODIS, for example. Now, then you have other missions. You can see here color-coded in white and gray future and current missions. You have several of them that have then higher resolutions, but then lower revisit. And each of these missions, of course, provide data that is quite suitable for certain applications. Now, constellr's trade-offs have been selected for the future mission to be at 30-meter resolution, and with a fleet of satellites would reach 1 day revisit time. This is another view of something of the similar information, but just to show it in a different way. You can see here small examples of data from Sentinel-3, from Landsat. We say 8+9 because sometimes we use them now in an interchangeable manner. And then you have constellr's data. And you can see how the spatial resolution, as it is higher, then you have more distinction of features. And of course, it depends on your application. One type of data could be more useful than another for you. But of course, the higher the resolution, the more features you might be able to see that could be more useful for the urban environment. You can also have differences with, as we said, with revisit, with frequency here that is indicated for these examples, but also in the number of bands that are being captured in the thermal domain, and so on. So how then have people used these relatively low resolution data sets to provide useful information? So there have been great accomplishments, and an example of them is what we will see in the next talk, of how we could use something as a 100-meter resolution thermal data set and get data that is really suitable for neighborhoods, for example. Well, you have to align a lot of images from different sources, and then you could sharpen the images. First, often, let's say, if it's Landsat, you're going from 100-meter resolution sharpened with 30-meter near sphere that is coming with the same platform. Then you can use alternative data sets to go to 10-meter resolution. So it's quite tedious to do that, but it is doable. It's just it could be really improved with better data if already the original resolution is better, and with a higher revisit time to improve the monitoring. So this is where constellr's dataset hopes to contribute to the storyline of the urban environment. Well, I will leave it now to the next speaker to explain how they take this kind of data and actually build solutions that support the urban heat island monitoring. Thank you.
Thank you, Elsie. It's clear from your presentation that satellite LST can provide us with some very valuable insights when it comes to monitoring urban heat islands. And the next phase we'll look at in terms of how that data can be used in indices by local governments. And so to answer those questions, I'm delighted to introduce Mattia Rigiroli from Latitudo 40. Mattia is a data scientist and pursuing a PhD in Earth observation. He is deeply immersed in the intersection of data science, AI, and computer vision, with a mission to harness technology for the greater good. Holding a master's in data science and a bachelor's in statistics, his academic journey is driven by a passion for understanding and preserving our planet through Earth observation technologies. Beyond his professional life, he's an adventurer who enjoys traveling, cycling, camping, and being in nature. So Mattia, how does Latitudo 40 use the satellite LST data that Elsie's just gone through for measuring and monitoring urban heat islands?
Hey, hi everyone. Thanks, Charlie, to introduction. So it's a pleasure to be here today to present our work in Latitudo 40. So Latitudo is an Italian startup based in Naples, and we born from a spin-off of the University Federico II in Naples in 2017, and now we are a team of more or less 20 people. So we have developed a fully automatized workflow that starts from collecting different satellite sources like Sentinel, 1, 2, and Landsat, for example, and other data like population data, population density. Then we apply our AI models that allow us to extract new data layers, new, let's say, map. And we apply also our simulation tool. Then we can apply the analysis module to extract KPI and other insights that we can serve with our data through our marketplace, Earth Data Place that we are finalizing in these days, and through our platform, Urbalytics, that you can see here in the slide, and also through our API for technical user. So basically what we can do is access more or less 8 years of environmental and climate trends and analyze risk and problems, and also extract KPI that we can monitor weekly or monthly, depending on the phenomenon, and finally suggest mitigation solution that can be very specific to the area of interest. So our motto is learn from the past, monitor the present, and make the best decision for the future. And we want to do that combining Earth observation and artificial intelligence. So these are our data layers. And you can see for the climate part, we have land surface temperature and urban heat island analysis, and also the heat wave risk map that we will see later. We have also an estimation of the land cover map that is very useful to see in the cities, area covered by build-up or grassland, cropland, tree cover, or water, for example. And for the greenery, we have estimation of carbon sequestered by greenery or the tree cover density, or for example, the greenery health trend that is very useful to pinpoint critical area of greenery that are in decay, for example. And then we have microclimatic performance index and Parkul Island that I will explain later. And finally, we have a super resolution algorithm for Sentinel-2 that is very useful to upscale the full spectrum of Sentinel-2 that is useful to for different use cases. So the first step to monitor urban heat island is extract land surface temperature. And in Latitudo 40, we have developed a proprietary machine learning algorithm that is able to upscale the thermal information of different satellite sources, like for example, Landsat. And in this case, we have upscaled the thermal information of LST, constellr LST at 30 meter to 10 meter. And you can see in the slide very good details and texture that are precious to monitor urban heat island in urban environment. So after obtaining land surface temperature at this scale, it's very important to identify rural area, because for obtaining surface urban heat island analysis, we have to compare temperature in urban and rural areas. So basically, we have developed a procedure to extract automatically these rural areas. And here you can see the example for the city of Milan. And basically, we consider the distance from the city center or the tree cover density and land cover classes to extract these areas. And after that, we can consider all the land surface temperature available for 1 month or 1 season, for example, for summer season, to extract the surface urban heat island index, that is an index between 0 and 100 that express the intensity of the phenomenon for the area of interest, for example, in this case, for the city of Milan. And lower values are value with low intensity of urban heat island, and value close to 100 are area with very intense surface urban heat island. So the next step is to move to a risk map, because basically surface urban heat island index express the intensity of the phenomenon, but not the risk, because basically we have to combine also population data and other data like morphology, traits of the area to extract the risk, because if no one lives in an area that suffer that has a high value of urban heat island, there is not a high risk, so it's not a big issue. But combining all this data allow us to extract an index that we named heat wave potential risk, that basically span from 0 to 100 and express the true risk in the city. And in the map, you can see darker value are value with high risk of heat waves. So the next layer that can help us to study surface urban heat island in the cities is the microclimatic performance index. That is a layer that is useful to measure urban green infrastructure effectiveness in mitigate the urban heat island effect. So basically, we extract different classes combining tree cover density and land cover classes to assess the impact of greenery. And then with the Parkul Island, we are able to extract park cooling effect in the city. And we have divided this island into typology. So major Parkul Island and minor Parkul Island that can have different cooling effect. So the next step is combine all this information in a unique visualization. So here you can see the heat wave potential risk map, and then microclimatic performance index and Parkour Island overlapped for the city of Milan. And you can see that critical area to be prioritized are highlighted because not covered by any, let's say, nature-based solution, and also are area with high risk. And this type of visualization can be very useful for urban planner or policymaker that want to have an idea of area to be prioritized for example, for new intervention. So until now, we have seen analysis at the city scale. We need to go to a local scale, to a neighborhood scale. And here you can see the heat wave potential risk in our platform for the city of Milan. And we can see that some hotspots are highlighted. So area where heat wave risk is very high compared to surrounding buildings. And the access of this granular data at 10 meters of spatial resolution is very useful to develop to develop localized solution, because we know that different neighborhood of the city has different characteristics and needs that cannot be overlooked in the city scale planning. And also this type of granular data allow to develop a stronger sense of community in our cities. So finally, the aim here is not stop at data, but extract actionable insight. So this process is very useful to transforming urban challenges into sustainable solution and make informed decision. So basically, to develop the more resilient city, we need to extract this type of insights that can be utilized directly by non-technical users. So here you can see in our platform, Urbalytics, some aggregated analysis that we can do on top of, for example, heat wave potential risk or urban heat island. So you can see the heat wave potential risk across city district. That is very useful to have a ranking of all the districts in a city with the mean risk, for example, or with other aggregated statistics. And for example, you can see in the image also the thermal comfort on bike path that is very useful to, for example, suggest to citizens the best path to follow, for example, during summer, during heat waves, or for urban planners to plan more cool, say, bike path. So this is what we do at Latitudo 40, and thanks for your attention.
Thank you, Mattia. And fascinating to see the number of different ways that you use that LST data for creating those indices, and the complexity and the other data sources that you have to fuse with it, and what the indices that you are providing to the customers. And it's clear from that there's a need for data from an LST perspective that has a higher native spatial resolution to enable you to help your customers to improve those indices and help them with their decision-making process with urban heat islands and the mitigation. And that leads on to terms of what does the future look like, based on what the needs we've seen today. And constellr, we're delighted to introduce our constellation of satellites that we will be launching later in 2024. This will bring a new standard of resolution for thermal infrared data from satellites with a native spatial resolution of 30 meters. And due to the cryo-cooled sensor developed by our founders, we'll have an accuracy with that of within 2 Kelvin degrees, and the ability within there to see differences of 100 millikelvin within a scene. And we will, with our constellation, be able to revisit those areas daily, meeting the needs that we've seen through the presentations today of more data to understand what's happening in urban heat islands and how we can improve them. And how that data will look like, we have generated a synthetic image here looking at the city of Toulouse in France and the type of data that we have. And this has been sharpened down to a 10-meter resolution to give a taste and feel of what we're going to be providing to customers to help with those urban heat island analysis. And the satellites will also have on them a visible and near infrared sensor with a resolution of 10 meters. And the benefits that this will bring is that we have the sensors, the thermal infrared and those visible and near infrared, on the same satellite. So helping to simplify that process of sharpening down to the resolution that's required for those urban heat islands by having that on the same at the same acquisition time as well, and overall improving and the sharpening of that LST. And how can people get access to that? So you can do so by talking to us about our early access program, and you can contact us, and details of that are available on the following slides. And this enables you to get early access to the data from our constellation that will start launching later this year. This is the ability to secure terms for up to 5 years, and there's flexibility of commitment within there. And we're really excited to speak to people to learn about your needs and ensure that you get access to the data from our satellites. And that concludes the presentations of our webinar for today, and we will now move on to our Q&A section, and we have that available in the Q&A tab at the top of the webinar band. So if you'd like to put it in there, and any questions that you may have. So the contact details for myself are available on this slide here. And so whilst we're waiting for those to come through now, I think I just have a question to Joachim, just regarding in terms of the uptake across Europe in terms of managing urban heat islands and policy. How do you see that? Is there a big uptake in terms of using the geospatial data? Is Joachim still on the call? I think he may have dropped out of that. So I think the next question I would go to Mattia in terms of, with your customers that you're currently working with, which indices are they most interested with at the moment?
So we work with different municipalities in Europe, basically, and they usually they don't have the technical team to address to access this data. So basically, they need actionable insights that can be really useful and easy to understand. So basically, what we can do is try to simplify the access to this type of analysis and data, and this is what we are trying to do. And also, we are trying to use this type of partnership to develop a new analysis that we can then, let's say, replicate to other cities. For example, the bike path analysis born from a project developed with the city of Milan, and obviously the idea here is try to replicate this type of analysis with other cities or their areas, because basically we see that this type of analysis are very interesting for not only for, in this case, Milan, but for multiple cities.
Thanks, Mattia. So we have a question in the panel. So the question is, the biggest threat of UHI to human health is not during daytime, but overnight temperatures. Will constellr have nighttime acquisitions when the SUHI differences are greatest? I think I'd put that question over to Elsie.
Yes, we will have nighttime temperatures as well that are being acquired. And at the same time, we are also working on developing the diurnal cycle modeling of the LST, whereby we acquire the data from all sources, including our constellation, and try to model in a continuous manner the temperature change during the day and night, because that will enable also actionable use of the data by our end users who often want to have it at the same exact time to be able to compare data sets. So it is still work in progress, but yeah, it is possible.
Thank you, Elsie. I think leading on from that, so Joachim, I think you dropped out for a second there. I was just wondering in terms of the uptake of monitoring urban heat islands and providing data. How is that progressing within the EU? Is there a fast uptake in monitoring the urban heat?
I would say there's two levels of it. I mean, it depends, I think, a bit on the governance level which you are targeting and then what tools are available. At EU level, we would be mainly interested to understand indeed, I mean, what's the current sort of magnitude of the problem and how is it changing based on time series data. I think that the main bottleneck there is sort of the availability of an off-the-shelf product that can be used by policymakers who obviously don't have remote sensing experience. So I think this is currently missing and therefore also hindering, I mean, further policy development on that front. I think we are for the managing of cohesion policy budgets, we are frequently in debate with regional authorities, typically, sometimes also urban authorities. What we see there is something that I also highlighted a bit in my presentation, is a lack of capacity with regional and urban policymakers to understand the data and the problems. I mean, they obviously they know about urban heat islands, but if you would ask them, okay, where are the problems in your cities? What can you do about this? Then there I think authorities and administrators they need their guidance and help, and I think, I mean, certainly companies like yours can do that. That might not be so maybe in the UK or Belgium or the Netherlands, but we are then thinking about countries where administrative capacity is typically low, Eastern Europe, for instance, but where there will also be a substantial problem in the future.
Thank you, Joachim. And we have another question that so this is a to constellr. Can we task your satellite, or if your satellite will just scan the Earth and we buy you the image from you? So we do have tasking capacity. So through our early access program, you can book tasking for your area of interest from there. So that is available. And a second question from there, is constellr commercializing by kilometer squared, scene, or subscription? And For that, we do it by a customer basis, looking at what your needs are and what you need to acquire and what works best for you. So to answer that further, we'd be happy to have a call to discuss that. And then a third technical question that the attendee says that they're using Sentinel a lot. Do your satellites calibrate with Sentinel? So yeah, do constellr's satellites calibrate with Sentinel?
Shall I answer that?
Yes, please, Elsie.
Okay. So indeed, we're taking Sentinel-2 as reference in order to co-register our data. And at the same time, our Vernier sensor as well is having what we call Sentinel-2-like bands, also to ease harmonization and to get also ease in performance. So in both sides, you saw the geospatial aspect and the band aspect. So are looking at Sentinel-2 in that sense.
Thank you, Elsie. And there's a couple of questions in the chat. So Mattia, on one of your slides, you mentioned AI processing chain and simulation tool. Could you please specify in what context you use that?
Yeah, thanks for the question. So basically, the simulation tool that is currently under development is developed for, let's say, simulate some intervention in urban areas. So basically, we have the possibility to submit some, let's say, vector data like tree lines or new pavement, etc., and create a synthetic Sentinel-2 imagery starting from this vector. And then we can, let's say, replicate our analysis to see if some intervention can, let's say, reduce the temperature or reduce the risk. So basically, we are developing this tool with also with the city of Milan for estimate the effect of an intervention before it is implemented, and maybe to evaluate the best one to be developed.
Thanks, Mattia. And then another few questions for you. So is the heatwave potential risk index standardized or normalized for different city types to compare them?
Mm-hmm. So yes, the index is standardized and can be compared between different cities. And I try to answer to the next point. If we have a paper on this index, not yet. We are working on that. And the Parkul Island measured by daytime. So basically, the Parkul Island, so the cooling effect of greenery is estimated not considering the, let's say, the temperature data, but basically only different traits of greenery like tree cover density or the distribution, the spatial distribution of the greenery. And we do, let's say, every year this type of estimation, but also for this type of layer we are currently writing say a paper to put together the analysis and the workflow that can be replicated to other cities.
Thank you very much, Mattia, for that. I don't see any further questions, so maybe there's one from another one that just came in. So it said super interested in the super resolution algorithm. Did you build the model yourself or use an existing model such as SRGAN? What did you use for training? What data did you use for training?
So I supposed to be the super resolution of Sentinel-2, not for land surface temperature. But yes, we developed a model that is able to upscale the resolution of Sentinel-2. Is trained, let's say, with pair of Sentinel-2 and other commercial imagery with higher resolution, target resolution of 1 meter. And this is very useful to let's say have access to the powerful of Sentinel-2, but with more detail, and is useful for certain type of application where maybe you don't need the millimetric accuracy in terms of details, etc. Because obviously, these type of results are from a GenAI model, so you cannot, let's say, have perfect data, but you can enable different and new use cases because the cost of this type of solution can be lower.
Thank you very much, Mattia. So we've now come to the end of our allotted time. Thank you very much, everyone, for your questions. And I would like to say a big thank you to all of our presenters. It's really been a really fascinating session that we've had today, learning about how we use LST in urban heat islands. And also thank you to everyone for attending our webinar. If you have any further questions, please don't hesitate to reach out to us and get in contact. And that concludes our webinar. And so I would like to wish everyone a good evening and good day. Thank you. Bye.
Thank you. Bye-bye.